This video gives a brief overview of the HBM eDrive system. eDrive is used to test inverter-driven electrical machines and delivers results that will give you new insights into the machine and its control. Like a power analyzer, eDrive acquires all signals like voltage, current, torque, and speed, and computes live power values like true and fundamental power, lambda, eta, or THD, just to name a few. But beyond this, it also stores continuous raw data for verification and detailed analysis, such as space vector or DQ0 transformation. The modular DAQ system for 12 to 42 voltage and current channels meets even the most complex test requirements for electric drives. It offers direct inputs up to ± 1000 volts, easy connection of current clamps or current transformers, and a sample rate of 2 megasamples per second per channel to catch high-frequency components in the signals. Combined with one or more world-class HBM torque flanges for torque, angle, and speed measurement, it forms the base of the next generation of test instruments for electric drives. For this demo, we will use a miniature test rig. Although miniature, it holds all components of a real test rig, 2 inverter-driven machines working as load and as device under test against each other, with a torque transducer with angle and speed sensor in between, and a convenient control for both speed and torque. The 3 line voltages from the inverter output are connected to the voltage inputs using the artificial star adapter delivered with the system. Current clamps are connected directly, while CTs are connected using high-precision burden resistors plugged into the DAQ's inputs. Torque, angle, and speed signals come from the torque transducer and are connected to the digital inputs of the DAQ using a breakout box. The setup sheet of the software maps the application with a power source, an inverter, and an electrical machine. Different configurations can be selected, such as DC input or phase-to-phase measurement. The integrated wiring diagrams ensure error-free cabling. Select a sensor from the built-in sensor database to configure the input amplifier, including sensor calibration data used for scaling the sensor output into physical units. Then, select the expected signal ranges for voltage and current. Finally, select the torque and speed sensor. Now you are all set to measure. The live sheet of the software shows traces and numerical results. In the upper half of the 17-inch display, meters are showing results similar to a power analyzer, and in the lower half, there is a scope-like waveform display. The scope can be set to different input signals or to individual phases, tracing the setting of the power meters. Zooming in on the waveform displays additional signal details if needed. An FFT display shows fundamental and switching frequencies at a glance. For more results, a configurable section with more meters is available. Here, over 50 computed parameters can be selected for live display. At any time, the Log to Excel button transfers all results straight into Excel. No storage, no conversion, no export. Finally, we store some data so it can be used for a more detailed analysis later. Record starts the storage, and we record this initial set point for a few seconds. Then we proceed to the next set point by increasing speed and again record for a few seconds. Then we decrease torque for the last set point. Finally, press stop to end the storage. Now it's time to review and analyze the recorded data. Starting point for all post-run analysis is the formula sheet. This is pre-filled with all formulas for basic power analysis. However, each user can change existing or add custom formulas. We start the review using the display sheet. It shows raw data for visual inspection with scroll, zoom, and cursor. Sheet Phase RMS and Power shows all entities of Phase 1 like voltage and RMS voltage, current and RMS current, and finally, true power in Phase 1. The sheet Total Power shows true and apparent power at the inverter output, the mechanical power, and the power loss in the motor. Finally, the motor efficiency is shown as a trace over time through the 3 set points we have recorded. All of that is available out of the box, no user programming required. But this is where the real journey starts. Based on the raw data, the nearly unlimited capabilities, and the more than 200 functions in the formula database, the user can proceed with any analysis he wants to do. Here are a few examples. You might do a space vector transformation of the currents and plot the resulting alpha and beta currents as a vector diagram, showing how balanced your control algorithm works both in general and during a load change. For that, you can play back the stored data. Or, if you recorded the motor position as well, you can do a DQ0 or park transformation to see the direct and quadrature currents as traces over time to understand the quality of your controller. Or you compute the magnetic flux in the machine and compute the torque in the air gap, an incredibly powerful tool for understanding hybrid drive systems, where direct torque measurement is difficult or impossible. The analysis can continue to generate equivalent electrical parameters, torque ripple, armature currents, magnetic losses, and so on. The sky is the limit. Beyond the powerful analysis capabilities, there are a few more important differences between the HBM eDrive system and a standard power analyzer. First, given the modular concept, you can increase channel count up to 42 to analyze complex setups such as multi-motor drives, multi-level inverters, eCVTs, or similar. Second, special DAQ satellites can be added to record temperatures. For example, winding temperatures to correct for the copper resistance, or CAN bus messages to give a better understanding of the inverter's reaction on control commands. Third, beyond result transfer into Excel or via software command, the optional EtherCAD interface delivers computed results with 1,000 values per second into your control environment. The HBM eDrive system is a new approach to analyze inverter-driven electrical machines. It continuously acquires all electrical and mechanical signals, including temperatures and CAN, in a single system. Easy to set up and easy to use. Analysis of stored data opens unknown possibilities. So beyond the pure efficiency measurement a power analyzer offers, it stores raw data and has all the tools to help you understand the losses and therefore to increase efficiency. The HBM eDrive solution. Nothing comes close.